I'm Jan-Peter van Zandberg. I work at the Netherlands Forensic Institute. In the past day, we already heard a lot about NAND-flash memories. And also, so it shouldn't be very surprising that everybody should know by now that's the dominant storage medium for non-volatile memory. I also did a very good job in explaining a lot about these errors. So the purpose of this research that was carried out is to investigate to what extent you could use these errors to your own advantage. So they are a nuisance because they might prevent you getting access to the data. But on the other side, it might also convey some noisy information about the data itself. So it can actually be beneficial, is the hypothesis. So in order to do that, I will go quickly over some issues of reliability and error sources in NAND-flash. It will be very quick because most of them were already explained by Aya. And then something about the data processing. So how do you get actually, in a real-life situation, access to the error information which is present on this NAND-flash. And then I will describe a number of experiments that we have carried out in order to verify to what extent the error statistical information about the number of bit errors is really, has some forensic potential. So first, very quickly, something about the NAND layout. So we all know about where we're talking about. So a NAND flash consists of a controller, USB device controller part, which communicates with the outside world. And the NAND flash itself is hierarchically organized. So it's divided into blocks, which is the smallest unit which can be erased. And each block is subdivided into a number of pages, which is the smallest unit that can be either read or written. So the page itself is already also subdivided in a number of smaller units. I usually call these data chunks, and each of these data chunks has its own extra part of storage, which is only available to the controller, which is usually called the spare area, which is used to store additional information about the NAND flash. So yesterday already heard it could contain some meta information about logical block numbers, but also ECC information is stored in that area. So this is a short overview of how NAND flash is organized. But as I already explained, you have different flavors of NAND flash memory. You have cells which contain 1 bit of information, single level cells, or you have cells which contain 2 bits of information. They're called multi-level cells. And you also have cells which contain 3 bits of information, triple level cells. But these cells are unreliable, so the content of the memory cell may change over time unintentionally. Now there are a number of processes. In the previous presentation already mentioned retention time, so if you keep data for some time in the memory cell, then the charge may leak away, which leads to a modification of the value stored inside the cell. And besides that, reading or writing of information might also modify the content of memory cells. And in this case, it might modify the content of adjacent cells. So not the cell themselves. If you read from a certain page, then information in adjacent pages can be modified. And it was also mentioned in the previous presentation, so the rate at which errors develop also depends on the quality of the NAND flash. So if it's repeatedly erased and programmed, then the cell deteriorates, which makes them lose their charge more quickly. So this is one of the pictures from the literature. So this is a graph. So on the x-axis you have the number of PE cycles, the number of times it has been erased, and on the y-axis you see the bit error rate for different sources of information, different types of errors. So the important things that you have to notice is that the retention errors are the largest in magnitude, so they contribute most to the bit errors, and also the rate at which errors develop also increases with the number of PE cycles. So that's important to notice. Now, in order so the NAND flash memory itself is an unreliable storage medium. In order to make it to make good use of it, then vendors have taken some measures in order to increase reliability. We also heard something about that in the workshop yesterday. So what the most vendors do is they use randomization, which means that data is written before it's written to NAND-flash, and in that way you can minimize the number of inter-cell interference, so the number of read and write errors can be less. And besides that, of course, error correcting codes are stored, parity bits are computed, which enable you to determine the number of errors which are present in the memory and also correct them. And besides that, because it's sensitive to the number of PE cycles, so the number of times it has been erased and reprogrammed, it's important to use all the memory pages in the whole memory so that they wear out at the same rate. So if you are very naive, you would always use the first page, so it will wear out very quickly. But if you spread it across the NAND-flash, then the lifetime of the memory will increase. So these are all things that are implemented in the controller. So when the controller writes data, then it does these three operations. It does wear leveling, error correction, and randomization. And that means that the actual data which is stored in the NAND-flash is different from what is sent to it by the host OS. So if you look at this, so we have the host OS, you have the controller, and at the right-hand side you have the actual storage medium. So if you want to put this picture on the NAND-flash, what happens is that the controller randomizes it, so it becomes gray, it's noisy, and it adds the yellow bar, which is the extra ECC information. So those are the two operations which are performed by the controller when storing data on the flash. And if it goes the other way, the inverse process. So the randomization is removed and the ECC information is applied, and then you get the picture back again. So essentially that is what happens when you store data on NAND-flash. But if you only look at the NAND-flash itself and you don't have any access to the controller, so the question is, you also heard something about it yesterday, then what you see if you read out the data in NAND-flash, you see data including randomization and ECC parity bits. So it still contains bit errors. So the question is, if you only have this information, can you go back? Sorry? Well, there are several possibilities. So yesterday we also heard some approach to remove randomization and to find ECC parameters. We do that ourselves also in a different way. At the first time, our experience is that most of this randomization is often produced by a hardware sequence called the LFSR, a linear feedback shift register. And there is a nice mathematical algorithm which is able to detect an LFSR, so that able to compute the feedback taps of an LFSR from a stretch of data which doesn't contain any errors. So this algorithm comes from coding theory, and it's called the Burlekamp-Messi algorithm. And we use that, we just apply that to our data and see whether it is able to detect an LFSR. And if that is the case, then we can make some additional steps, and then we can find an LFSR is a structure of a number of cells, and each time the cells are clocked, then data is shifted in it. So you have two parameters. You have the feedback taps, and besides that, you also have the initial filling. So if you do some further research, once you've found an LFSR, you do some further research, then you can find out how the register is seeded. And for the reconstruction of the ECC, the main problem is that if you want to recover code parameters, then you have to get access to a number of code words of which you are certain they don't contain any errors. That means that, and if you only have a raw dump to work on, then you can never be sure which of the code words are, which of the data you get from the NAND-flash is without errors. So in this case, we make an assumption that we use a cyclic code, which is not a very strict assumption because most of the codes which are used in NAND-flash are cyclic codes. For instance, BCH codes are cyclic codes. And then we search stepwise for some technical parameters of that code on the basis of our data, and we have a method which is can figure out itself which of the data doesn't contain any errors and is valid data. So it's tolerant for the use of incorrect data. And once we found that, we determined the parameters of the code, so how long the code words are, how many of them are, and the number of errors codes are able to correct. And after we found that, we also look whether that the code parameter that we found belongs to a BCH code, because there are very quick, dedicated methods for decoding BCH code. So that's in short the possibility. So this question we can ask, we can say it's affirmative. So in certain cases, when we only have the data from the NAND-flash, then we can recover all the randomization and ECC parameters, and then we can recover the picture again. With thanks to these three people. So I will point out. So the first two are Berlekamp and Messi, and the last one is Euclides. He's a mathematician from around 100 BC, and we use his algorithm in order to compute the code words. So he invented an algorithm to compute the greatest common divisor of two words, and that's essentially the method that we use in order to compute some parameters of the code. So if you are interested in that, I've written a paper some years ago about it, so if you really want to know all the details, then you can ask me afterwards. So back to our research question. So if you have access to these bit errors, can they be used for forensic purposes? So the first thing which is important to notice is that these error sources are related to potentially forensically interesting processes, so such as retention time. So it's the time that some information has been present on a certain location within the memory. And besides that, also the number of times it has been read or read also. So this is potentially forensically interesting. But the question is, in a forensic setting, are these sources large enough to change over the periods where we are interested in? Typically in a forensic investigation, you are interested in changes which occur over periods of weeks or months. So the question is whether any changes in bit errors occur on those time scales. And also, in a more realistic user scenario, to what extent are these activities, can bit errors be related to the activities that are actually performed on a NAND flash? So in the first case, we performed an experiment on raw NAND flash memories, which were written directly. So we didn't use any controller to write. We wrote directly to the NAND flash memory itself, and we didn't use any ECC information. And we prepared memory chips, so we created different regions in the chip which underwent different number of PE cycles. And afterwards, after preparation of this memory, it was programmed with fresh random data, and then it was stored at either room temperature or a somewhat higher temperature, and then we watched the rate at which the errors developed. And in this case, it's very easy to compute the number of bit errors because you know what information is written to the memory itself, and if you then compare with the information that you get back when you read the memory, you get directly the number of bit errors. So this is one of the pictures from the paper. So below, I've indicated the different regions which have been created in the NAND flash memory, number of PE cycles to which each of these regions has been subjected. So according to a manufacturer specification, the number of PE cycles for this NAND flash memory was 5,000. So these numbers are relatively low with respect to the manufacturer specified number. So what you see, so this is the results for a NAND flash which was stored at room temperature, and this is the result of a NAND flash which was stored at 70 degrees centigrade. And the different colors, they denote different times. So what you see is, important thing is that you see that over time, so if you go up, the number of bit errors increase, both for the higher temperature and also for the lower temperature. But the error rate at the low temperature is much lower, as you see here from this axis, from the y-axis. And the same thing that you have to notice is it also depends very strongly on the number of PE cycles. So in the regions outside, which were not stress cycled, you see that the rate at which errors develop is much smaller than at this region which underwent 2500 PE cycles. And the time scales, it's indicated above, so it's in the order of weeks to months. So actually, what you see is there are detectable differences in bit errors over periods of weeks to months, both at room temperature and also at higher temperature. But the rate strongly depends on the temperature, as you saw in the previous slide, and there's also a rather big effect of the number of PE cycles from the regions. And for forensics, that's also important because sometimes if you do experiments on a reference device, it's very new, it's only used a limited amount of time, and if your method works for that, if you apply it, for instance, to a case, then you might have a device which has been used for an unspecified number of times. So the effect of, for instance, heat or other things might be much larger for that other device because it underwent a sizable number of PE cycles. Now, for the second experiment, we used a very advanced setup, which is shown here. It's a heating stove in which a glass container is, and there we keep some USB sticks. In this case, we performed experiments by using the controller, so we copied files onto the USB device and did a certain protocol, which I will explain afterwards. And after that, we removed the NAND-flash from the USB device and we read it at the end of the experiment, and then we processed the dump, which means that we de-randomized it and we decoded it, and then we got statistics from the number of bit errors. And after that, we checked for a relation between these statistics of bit errors and the actions that were performed on the device itself. Okay, so the protocol consists of copying different files at different times to the device. In between, we stored at either room temperature and 70 degrees. And we did two things. First, we did the data retention. We only copied at different times files. And we also tried some stress cycling, which means we first copied a number of large files onto the device. And after that, we repeatedly copied the same file a number of times to the remaining area. So we assumed that was stress cycled. And afterwards, we copied another number of smaller files onto the device. And after descrambling them, we were able to allocate memory pages onto a specific file which has been copied onto the file because we computed piecewise hashes of the original data and compared it to the hashes of the descrambled memory pages. So just this is a typical example. This is not from the paper, but from a slightly different one. So here you have the page number, and on this side you have the number of bit errors. And in color code you see different files which are copied onto the file, onto the thumb drive. So the order in which it occurred was first the blue one was copied, then simultaneously the green and the red one. And after that, this device was stress cycled, and after stress cycling, two other files were copied. So the light blue one and the last one copied onto the file was the purple one. And so that's the order. And the important things to notice is that you see the wear leveling algorithm because this large file is spread over to different locations within the NAND-flash memory. You see some effect of retention time. So the blue one is the first one to be copied, and it has slightly more bit errors than these were copied afterwards. And the last one, this one here, has evidently less bit errors. So there is some effect of retention time. So they're not totally random. And after the black dots, this is noisy signal, so we average it over the size of a number of pages from which we had no documentation in this on this chip, so we average over the size of 256 pages, which we assume to be the size of the block. And due to this averaging, you see more detail, so noisy signal becomes less. And also, you see some effect of this stress cycling protocol that we did, because if you only copy files, then they're stored onto a fresh thumb drive. They're stored more or less sequentially, but those files copied after stress cycling are more interlaced, so there is some effect of this stress cycling protocol. So now to the actual data. So we did 4 USB sticks, two two were scored for the data retention protocol, both at room temperature at 70 degrees temperature. So this is the same picture. But the important thing that you must notice is that there are large differences between individual thumb drives from the same batch. So the base error level for this one is larger than for the other one, and they are both stored at the same temperature. Also, if you look at data from room temperature, you can also see, if you go back, so that sometimes even the area which was used for data storage can change. So the upper one uses a smaller area than the other one. But in this case, you see more or less the same. So by stress cycling, it's more the files copied after stress cycling are more interlaced, while files copied without stress cycling are stored sequentially. So the conclusion is that there are large differences between USB sticks from the same batch, both for the area of data storage and also the baseline error level also varies. There appears to be a slight relation between the time at which files are copied onto the drive and stress cycling does something because of the area which are used. Now, for the same thing, you can also use this information to form some histograms. So at this time, at the x-axis, you have the number of bit errors, and at the y-axis, the number of times it was found, and the color coding is the same for files. And as you see, for instance, for this time, so on the basis of the number of errors, then you can group the files, the memory pages belonging to one file together. So that's still 1 minute. So the thing I wanted to tell you is that if you do low-level acquisition and offline analysis, then you can get access to an independent side channel of a normally functioning device. So the device was not broken, so it worked normally. And possible use of it is that it could be used as an independent side channel, and maybe you can use it to perform some relative dating. So say something about some memory pages have been longer on the NAND-flash than the other one, and also maybe, as I showed in the previous slide, it can be used to group memory pages. But we are the Forensic Institute, so we should be very careful. At the moment, it's just academic research, not fit for users in cases. So there are many factors affecting this bit error statistics, which means that I only looked at the moment at retention errors, but there are many other ones which might occur simultaneously or concurrently. So, and also you have this effect of either retention time and PE cycle. So if you have a file which has been on a bad piece of the memory for a short time, it might contain the same amount of errors like as a file of a piece of data which has been on the better piece of the NAND flash for a longer period of time. So I think that this was my last slide. Okay. So this is where we stand at the moment. So we did some initial research, and in principle we would be interested in any cooperation or any additional ideas that you might have in this respect. So thank you for your attention. Thank you.